Hello, this is the lecture on manufacturing processes and operations. Well, first, let's look at this overview of manufacturing processes. Depending on what type of the work we are doing, and it can be categorized into different aspects. So, for one thing, is shaping processes. For example, if you want to shape the workpiece into certain geometries, you can use, for example, machining, deformation processes, or solidification, or particulate processing processes. If you want to enhance the properties of the workpiece, for example, mechanical properties, you can use treatment. That's another type of manufacturing processes. It also we can use some processes to clean the surface and also to manipulate the properties of the surface. And another major type of the process is assembly. So there are two kinds of assembly. One is permanent joining, for example, welding, brazing, and adhesive bonding. Another type of assembly process is the mechanical fastening. So in this lecture, we're going to have a survey of all these processes, and you will see you will need to watch a lot of videos because only by watching this video that you can see how these processes work. And first, before we get into each of the process, we need, there are different considerations that when we decide how to choose a manufacturing process. For example, if I have a part like this, and then we start to think about, okay, what manufacturing process can I use to make it? Someone may say, yeah, I can do machining, maybe casting, or 3D printing, right? Well, yes, all these processes will work, but it also really depends on, is it a plastic, right? If it is a plastic, think about what process we can do. Yes, we can do injection molding. We can do a machining. Either use the lathe or use a CNC milling center. We can also do injection 3D printing, right? Like this. And all right, so that's the plastic. Then what about is the metal? So for metal, and yeah, a typical process will be do machining, and also we can do casting. But can we do 3D printing? Someone may say yes, of course. For a lot of metals, it can be used as we can use 3D printing to make this part as well. But think about the cost, and also not all the metals can be actually can be used to make this part. So when we are, when we have a part, we're trying to find out what kind of process, to make it. One thing is materials. Now we know, either plastic or metal, but within each category, we have to think about, okay, which plastic, right? Because there are also many different kind of polymers, like we discussed in our prior lecture, right? Thermosetting versus, thermoplastics. The process may be different. For example, in thermoplastics, we can do injection molding because we can melt them. But what about thermosetting? Well, you cannot melt them, right? It will burn. And in that case, you might have to choose some machining processes. Same with the metal. Depending on the metal, some metal may be easier to machine. Some of the metal may be hard. Maybe some metals we can easily do casting. Some metals we probably have to do machining. So this is one consideration. It's materials. Well, the second one is tolerances, right? Depending on the part and what tolerance you are looking at, the process choice will be different as well. For example, if we have if we define tolerance as plus minus 0.01 inch, well, and we know what kind of material it is, and then now let's look at what kind of process may work, right? 0.01 inch as a tolerance. Yes, we can. If you look at this part, we can use sand casting. We can do we can do machining as well. It can also give us that tolerance. However, if we are looking at some cast iron processes like this, right? And then it may be a little bit hard for us to get into the tolerance of 0.01 because their tolerances are at plus minus 0.06, and it's in the incrementation of 0.06. So so now this is the tolerance difference, and we have separate options. Then if we define a tolerance of 0.001 inch, for the stainless steel material, then which process we can choose? Well, probably all these, sand casting, machining will not work because it cannot really get into 0.001 like this one. The milling and turning cannot get into 0.001, and then abrasive process, yeah, they will get us into the 0.001 one tolerance, and also some non-traditional process, can also do that as well. And in this case, we will have to think about how which process we need to choose. Not only the functional and the quality on that aspect, but also we have to think about the cost, because all these process will, the cost of those processes vary a lot. And another consideration will be, for example, when we have the part, we have the several processes to choose. We have the machining, casting, or 3D printing. Suppose that we are, they all can make the same, get into the same tolerance. Well, in this case, which process should we choose? Should machining or casting or 3D printing? Well, say if we want to do the machining, so on the left, this is the CNC machining center, while on the right, this is a 3D printing center. As you can tell, that the cost for the CNC center is only $20,000, but the 3D printing, metal 3D printing center is actually $500,000, and that is a basic level or for the metal 3D printing. So when you are choosing the process equipment, the cost of the process is another big factor you have to consider during that. And another consideration you may want to think about is the number of work pieces and also the design of it. For example, this is the Tesla car, and this rear underbody shapes. Original design, it has 70 pieces. Well, after revision or making a change of the process, they actually make it as 2 pieces. So you can see in this design, there are going to be a lot of sub processes getting involved in make each part, as then assemble, join together, either use welding or some other processes. Well, for this, for the second design, mostly it's a casting process that will make it make this big part. So you can compare the cycle times as well as the cost of the process itself, because if you have multiple processes, you have to spend money on the labor. You have to spend money on the equipment as well. And if you add it up all together, with many processes, then that's a big cost. Well, if you only have 2 processes, which means that you only need to build 1 process, although the cost of that for that process may be a lot higher than each one single process in the first design. It can be more economic than 70 pieces, because if you have 70 pieces, the chance of malfunctioning is actually getting high, because there are going to be a lot of interactions between all these parts. Therefore, this is a summary of some of the considerations you have to think about, and something to know is that these are not all the considerations. There are going to be a lot of other considerations, depending on the your design situation, the environment you are working, safety, all the other things. But these are the common factors you may have to consider when you are choosing manufacturing processes. All right, now let's get into our next part of the lecture, which is the shaping of polymer materials. So for polymer materials, mainly we're looking at the thermoplastics because we can melt them and then reshape them into geometries we want, right? By using some mold. And so mainly we're looking at these processes, solidification processes here. And the first one is the extrusion. So extrusion, basically that's extrude materials, right, through through a barrel, and then there will be a screw, and the screw will carry on the material to the end of the barrel, and then it will push the material through a die, right? Through a die, and the material come out of the die will be called extruded, right? So this is how the extrusion process works. And if you get into details of each single part of the of the equipment, you can see here is a hopper, where this is the place where you feed the materials. Typically, these are the plastic pellets. After the pellets get into the getting into this barrel, and the first is it's the feeding section. So basically, to give initial heat. So these are the heating pads, right? These are the heating pads to provide the heat of the barrel, so we can melt the pellets. Well, the initial the first section is the feed section, which is to feed the materials and heat the materials, and then it will and a screw, by turning a screw, the material will be pushed to the right, and then it will enter into the second section, which is compression section. In this section, some of the extra airs will be extracted, and also the material will be further heated into a liquid state. And then after that, it will get into the third section, which is a metering section. The purpose of this section is to make the material or all the plastic melt to be homogenized. So so when the material is coming out from the die, it's actually be more uniform. So this is and also start to build some more pressure in this section. And here is a breaker plate. So the function of the breaker plate is to make sure materials coming out from here will actually all having the same direction, right? Having that same direction, because when they are in the barrel, because of the screw is actually the turning function, the forces and directions of the moving of the melt is actually at all different directions. But once they go through this breaker plate, it will actually all the directions and the forces will come into the same direction. So this is the function of the breaker plate. And then after that, it will come out from the die, depending on what the size of the die and also the shape of the die. You can make a different shape of the extruded. And please watch this video so you can see how how this process works. And another process is injection molding. So injection molding is actually similar to extrusion. The difference is at the end of the process, instead of having having a die and then I'll come out extrude. Actually, the end of that is a mold, and also on the other side, it has a certain give a certain pressure to inject materials into the barrel. These are the these are the common material, the parts, or the products that can be made from the injection molding process. And in industrial injection molding process, and many of those actually have really be large size, and so like this. So this part is the injection unit, so which is to inject the material, right? Inject the material this is to inject to close and also clamp the mold and then open the mold. And this is part is actually injection unit. All right, so now let's look at the setup. And as I just mentioned, this is an injection unit, and this is a clamping unit. Similar to the extrusion, then the hopper moves here, and then the material is fed through the hopper, and then the melt, plastic melt, will be removed from left to right, and then through this nozzle. And then after that, what happens is the injection, the clamping unit will first be closed, and then the material, will be injected into, the shape. This is the mold where the shape of the product is. And then after injected, what happens is the ram will be retracted, and then the clamping unit will open. You will get a part. So this is the whole injection cycle. And you can watch all these videos to have a better understanding of the process. And so this is the first stage is the mold is closed, and then melt is injected into the cavity, right? Injecting into the cavity, and see this it's filled with a polymer melt. And the third one is the screw will be retracted, and then the clamp or the mold is open, so the part can be ejected. So this is the injection molding process. And another process is also molding, but it's called blow molding, which is to typically we are making some of the water bottles like this, right? Where we know that water bottles are in the middle is actually it's hollow, right? So how can we make those hollow shapes for bottles? That is we are using blow molding. It means why we call it blow molding means we are blowing air into the mold, right? Into the mold, and then to shape the product. And please watch this. Please watch this video so have a better idea of how this blow molding is used in industrial manufacturing processes. Another type of solidification process is to deal with the metal materials. And typically, we in metal shaping process, we call them a casting process. And how the casting process works is, first we have a pattern. Pattern means that is the product you want to make, but it's not a product. It's made some other materials to create the shape of for the product that's used in the mold. And also sometimes we may need to make a core. The core is used when there are some hollow shape geometries in the product. And then also by the mold is actually made of sand, so that's why we call it sand casting, right? The mold. So we need to have a good preparation of the sand. It also depends on the quality of the product. It also depends on the quality of the sand, and also how compacted the sand is, because sometimes there may be air get into it, or it's too loose or it's too tight. They're all gonna have some problem. And then after we have the mold, what happens is we need to melt the raw metal and then pour it into the mold. And then after that, we can start, wait a little bit until it's solidified and cool down to the room temperature. And then we can remove the sand mold and get the part. You may get in. There may be some of post-process cleanings getting involved in the process, because sand casting typically does not have really very fine surface finish. Sometimes there may be some other surface finishing processes following that. And this is the pattern. The pattern is typically made of wood or metal or plastic, right? So basically, the idea is to create the shape, so you can create the the geometry in the mold. So it doesn't really matter that much of how what the pattern is made of. And another process for the casting is we call it expanded polystyrene process. It's also called lost foam process in our lives. So what happened is, for example, we use a foam to create a certain pattern, and then and then we either we can use some sand or use some other material. For example, we can make the one in soil, right? Soil can also work. Just to use either a foam or some other material, as long as it can be melted, right? It can be melted by the molten metal, right? So what happens is the pattern will create the shape in the mold, and then when we pour the molten metal will melt the pattern, and then we'll start to create the shape that of the pattern. So this is how the lost foam process works. Just watch this video and take a look at how it is used in our lives. And this is a process. Typically we actually spray a refractory compound, outside of the pattern, the surface of the pattern, and then we put the pattern into the mold box, and then you can use the sand or some other materials in it, and then we pour the molten metal to replace the pattern. During this process, the foam or all the material that is melted will be vaporized. Typically, we use the foam, right? Vaporized, and we can use this process to make, for example, the engine block. And so the problem with sand casting and also lost foam process is that every time we need to make a new mold, because think about the sand, right? You get a part, you finished, and then you have to break the mold, because otherwise how can you get out of the part? And well, that is really a waste of time unless you are doing a lot of customization, right? You are not, it's not a large high volume production. Well, if it is a high volume production, what we can do is we can use this permanent molding process, right? So it will be similar to the injection molding we just talked about for plastics. So what happens is, here is the mold unit, and then of course you can actually create the core, so which is the hollow geometry for the products. And then what it does is, you start to pour the metals into the mold, and then this is how you can create the shape of the product. And using this process, we can always use the same mold for multiple products, and also it actually increases the efficiency of the process, because it reduced a lot of the cycle time, and we don't need to make a new mold every time we make a product. All right. Now let's look at another type of the shaping process, which is machining. And similar to all the manufacturing processes, machining also has its own family tree, because it can be categorized into some traditional machining process like turning, drilling, milling, and also some of the machining process are actually more of a treating the surface. For example, grinding, right, processes to make it more smooth, and our surface finish to be better. And also there's another non-traditional machining processes, which is to other energy sources, right? Either electric sources or chemical machining. So these are the kind of non-traditional machining processes. And EDM is another one. But in this course, mainly we are focusing on these processes. All you need to do is to have a general idea of how they work. Some most important machining operations are turning, drilling, and milling. I would assume most of you are already familiar with this process, but we'll look into some other aspects of those later. Some other machining operations include shaping, planing, broaching, and sawing. These are the videos. Please stop and then watch the video first, and then we can go on. Okay. And something to pay attention to is during the machining, typically we have a wrapping process and also finishing, because the surface finish and also the cycle time can be different during the operation. Why? It's because when we have a raw workpiece, and we usually start with the wrapping process, which is to remove a large amount of the materials from the workpiece, so we can get really close to the finish, right? And then because of the wrapping process, we do not need to set very accurate or very accurate dimensions or for that operation, for the wrapping operation. Because all we want to do is to remove molded material and get close to that. Typically, we use high feeds and also high depths of cut with lower speeds, right? With a lower speed, because if it is higher speed, a higher speed of cutting usually gives a better surface finish, but also it will consume more energy, right? Well, higher feeds, what happens is, think about higher feeds. That means that every step of the cutting, you are actually removing a lot more materials, which means that it requires more energy and more torque. And higher torque and more energy, it might cause your tool to break, right? Yes, so that's why when we are doing the roughing process, we may want to have higher feeds and also higher depths with some really hard tools, high strength tools, but with lower speeds, because at this point we do not need to consider the surface finish. Well, then after the wrapping process, and when we get into really close to our geometry, and what we want to do is to have a finishing process, which is to create the final part geometry. Then we need to be very careful about dimensions, tolerances, and also the finish. Typically, in this case, we will need to do more lower feeds and lower depths, because with lower feeds and depths, we can easily control its dimensions, right? But with higher cutting speeds, because the higher cutting speeds, it can result into a better surface finish. Now we are looking at the finished product. That's why we want to have higher cutting speed. And for a turning process, typically, for a turning process, the machine we are using is a lathe, and you can create multiple geometries or different types of the turning. on the lathe. One is facing, which is to remove the material, and then to a certain, and then another one is taper turning, contour turning. You can do make a shape, contour turning, and also we can do a form turning. Form turning means that you will create a cutting tool that is the same shape that you want to create on the part. So this is a form turning. And of course, you can do drilling as well. So turning, the workpiece typically is a round, workpiece that then by rotating a spindle or rotate spinning, and then it will create a round shape of the part. And chamfering, of course, to create the edge of the of the end, and also we can do a cut off, with this tool. And another one is we can do make threads, right? Make threads by moving the tool, up and down, in and out, and we can create those threads. Also, we can make some internal, right, geometries with this kind of boring process, which also involves using a lathe to turn or the part and let the part spin. And this is a setup, typical setup for engine lathes. And there are different parts of the or components of the machine. Here is a speed control, where you can set up the the cutting speed, and here or cutting speed or the the spindle speed, how fast the spindle spins, right? And this is the feed control. You can adjust the how much it moves that every step. So this is a feed, and also depth of cut. And so this is a spindle, and typically what we do is we're gonna put on use a clamp to hold the part, and then when the spindle spins, the part will spin as well. And where's the tool? Tool is set up here. And then by one motion is spinning of the part, another motion is moving of the tool. Then using the combination of the two motions, it can help us to create the geometry of the product. And the tool can move left and right, and in and out, right? So both directions. And when we are, another process is the drilling. We're all familiar with drilling. Just one concept is there are two types of the holes. One is a through hole, the other one is a blind hole. So if it does not go through the whole workpiece, means that is that's a blind hole. But if it went through the whole workpiece, then we call it a through hole. Like this is a through hole because it went through all the way out. Right, and for this one is a blind hole because it didn't really go through the part. And this is a drill press. So a spindle to spin the tool cutter, and this is the adjustable head. You can adjust the the tools up and down. This is the work table. This is the base. And some of the operations you can do with drilling is, for example, reaming, tapping a hole, or counter boring, counter sinking to create some, center holes. And also you can do the center drilling as well. And also you can do the spot facing, right? Spot facing with drills. And another machining process is the milling. So for milling, really there are two kinds of milling. One is parallel milling, which means that you can see the axis of the tool is actually a parallel, right? It's parallel to the workpiece, right? So workpiece, and then this is the rotation of the tool. By rotating the tool, you can see the cutting edges will remove the materials, right? Will remove the material. So this is called parallel milling. Another one is a face milling. So face milling, you can see the cutter is actually perpendicular to the surface, perpendicular to the center axis of the cutter is perpendicular to the workpiece. Those are milling processes, and some of the shapes or geometries can be made with parallel milling. Like the first one, we can make a slab milling to machine the whole surface, right? Or we can use this kind of tool to make a slot, right? And or we can do machine the edges with the tool, or we can do a strato milling like this, or form milling. And for face milling, of course, we can if the tool is big enough that is bigger than the workpiece surface, then we can do this workpiece face milling, or we can do a partial face milling to make it every time we remove a certain portion of the workpiece. And another one is use the end milling. So end milling typically give us more flexibility, machining the different geometries of the products, because they can move here and there and up and down without destroying material from other places. Like this, if the tool is too big, the flexibility of the geometry is actually a lot lower. But then milling kind of overcome that kind of difficulty and give you a lot more flexibility in making geometries. And the last type of the process is manufacturing process is the assembly operations. And for assembly operations are also can be categorized into two type of the assembly. One is the permanent. So for example, welding process, brazing, soldering is all permanent. And another type is the fastening, right? Mechanical fastening. So we are familiar with those when I use some screws, right, to fasten all of those. And first, for joining processes, for permanent joining processes, usually the joint is created, but it cannot be easily separated, right? Like welding, you cannot just use the screw, right? And then take the screw out and then separate the part. Then that is assembly. That is, a mechanical assembly. But for joining, like welding, you have to either break it apart or to separate the different components. And of joining types, these are the typical types of joining, like butt joint, right? Or you can do a corner joint like this, or overlap a little bit, or do the T shape, right? Joint, or the edge, right? Edge joint. And then for welding types, for different joints, for example, this type of one is we can call it the fillet weld. And if for the two, here is more creating a certain groove, right? So it's called groove welds. Or we can also do a slot weld, right? Plug or slot weld to join the materials. And so for welding processes, the material that we weld, we use is also should be the same, material as the workpiece. Well, if it is different materials, what we call them brazing, right? But for welding, it should be the same material. And well, for welding, let's look at the different type of the welding. One is the fusion welding, another one is the solid state welding. So fusion welding, which means that we are using the energy source will be from electricity, like arc welding, right, resistance welding, and oxygen fuel gas welding. Starting with arc welding process. So this is a typical setup of the arc welding process. first, we all we want to do is to create our circuit, right? Have the current to flow from from this positive to the negative, and then we can. This is the electrical cable to get connected to an electrode holder, and electrode holder will hold this electrode, which is the consumables, typically the same material as the workpiece, and then the filler metal. Sorry, the filler metal is the same material as the workpiece. Electrode is the one that provides the heat. Okay. And then we'll create an arc. When the arc will melt the filament metal, and then to form some have the filler metal melted filler metal to fill this gap. This is how we can weld things together. Okay, and here's the clamp to close the loop here. And another arc welding process is our typical arc welding process is called shielded metal arc welding. So the typical setup is that we have a consumable electrode in the middle, but outside we actually have certain electrode coating. So the coating is made of the materials that when it's melted, it can create a protective gas. So the purpose of the protective gas is to protect this environment from oxidation, because these are melted metal, and melted metal can easily react to oxygen and then create some of the materials or defects. So that's why having a protective gas will actually protect the quality of the welding. And please watch this video to have an idea of how this shielded metal arc welding works. And another process is the gas metal arc welding. So this is the setup of the gas metal arc welding. Different with the shielded metal arc welding. Gas metal arc welding actually provides a certain shielding gas, right? Shielding gas. Instead of using those coating materials, here is using a shielding gas. Typically, these are the inert gas, right? For example, argon. And this here it will have a spool of feeding material. Typically, that is the consumables, right? Consumables. And you can tell that for the shielded metal arc welding, every time you need to use those kind of filler metal, right? Filler metal, and that one is discrete. So which means that after you use one, you have to replace to another one. It's not continuous, but for the gas metal arc welding, because we can have a kind of a spool of feeding materials, we can make it as continuous process, which is more convenient and also reduces the cycle time. And here is the electrical wear, and this nozzle, and we can then the shielded gas will be created. So this is the gas metal arc welding. And because it's arc welding, so there's always a lot of safety issues related to the welding itself. For example, the arc kind of gives off a UV light. It kind of cause harm to our eyes, and you need a really good eye protection, right? And even without those, it might cause some chronic eye problems. If you work a long time while welding, I have to staring at it. Also, the fuse combustion, like it will produce the fumes. Those kind of fumes can also create some of the health concerns. And energy safety, electrical energy safety as well, because the arc, it might burn you, right? And also the flux has environmental issues. Well, another type of the process will be the resistance welding process. So these kind of process typically use electrical resistance to the flow of the current, right? To create the bonding. And For example, a typical one is a spot welding, right? You use electricity to melt a very small spot of the two pieces, and then by having the current to move through the two pieces, it will create a bonding, between the two parts. So this is the spot welding. Similarly, you can use the similar process, but you are making a whole line. If you're doing a whole line, that's called seam welding. Watch those two videos, you will have a better idea. And also you can watch the video about the projection welding as well. So this is the resistance welding process, right? And when electricity is is on, and what it does is, here we'll apply a force. When a force is applied, here a heat will be generated, at this spot, and then by melting or heating, this spot, it will create a bonding between the workpieces. So this is how it works. And there are advantages and drawbacks for the resistance welding. So the advantages are we do not need to fader metal required, and that kind of saves us money and also saves us a lot of extra steps for the process, and also we can give us higher production rate, right? Possible. And because every time we just make a spot, and then it's very fast. It's just one moment thing. It does not need a long time, and we can do automation, because it's the process operation itself is not very complicated or complex operations, and we can easily do automation with it. And it's good, repeatability and reliability. But the problems are these equipment are typically very high cost, and they're at the very beginning going to be some high investment when you are making or creating this process. And also the shapes, and the joints types will be very limited for resistant welding. For example, mostly our spot welding and also seam welding. And another type of the process is the solid state welding process. So what it does is, here we can see, one is with the static, the other one is rotating or spinning. By having this rotating and to move forward until it meets with the static part, and it will start to a certain force, right? With this high force, it will create the heat, at the interacting surface, and then that heat will start to melt the metals, and then to create a connection or bonding between the two workpieces. And this is how the friction welding works. And you can watch this video to have a better idea of how it is used. Another type of the process is within a solid state is the ultrasonic welding process. So by creating really fast waves or vibrations, those kind of vibrations can also create certain heat at this area, and then with that kind of heat, it can also start to melt the metal and create the bonding between the two. So this is the ultrasonic welding. Same, please watch this video. And that I mentioned before, for this lecture, you really need to watch all these videos to have a better idea what this equipment look like and how they work, and what type of products they can make. All right, so that's all for today's lecture.